Hello everyone, in this video I will be discussing on type 1 problem of Pelton wheel turbine. So here is the question. A penstock supplies water from a reservoir to the Pelton wheel with a gross head of 500 meter. One third of gross head is lost in friction in the penstock. The rate of flow of water through the nozzle fitted at the end of penstock is 2 meter cube per second. The angle of deflection of the jet is 165 degree. Determine the power given by the water to the runner and also hydraulic efficiency. Take speed ratio as 0.45 and coefficient of velocity as 1. So this is the question. So in this question we need to find the power which is given by the water to the runner, and also we have to find the hydraulic efficiency of the Pelton wheel turbine. So this is the first type problem related to the Pelton wheel turbine. Totally we are having two types of problem here. One is either you have to find the power and the hydraulic efficiency, and in the second type of problem we need to design the whole turbine. So basically here we are not designing the turbine, here we are just finding the hydraulic efficiency and the power which is required for the turbine. For this type of problem, let us see what are all the steps that we need to follow. So before that, let us write the data that is given to us. So here the gross head of the water is given. So let us consider Hg be the gross head of water of a turbine, that is given as 500 meter, and then one third of the gross head is lost in friction in the penstock of, that means while the supply there is a loss of water, that is about one third of the gross head. So here the friction loss, that is the loss due to the friction in the pipe, is given. Hf is one third times of Hg, and then the rate of flow of the water through the nozzle is given, that is of 2 meter cube per second. So here the discharge which is coming from the nozzle is given, that is the value of capital Q is given, which is of 2 meter cube per second, and the angle which is made by the jet with the previous direction is given, which is nothing but the deflection angle. So that is of 165 degree, and we usually represent deflection angle with the symbol theta, and the value is 165 degree. Here the speed ratio is 0.45 and the coefficient of velocity is given as 1. So we usually represent coefficient of velocity with the symbol Cv, and the value is 1. We can either express speed ratio as phi, or sometimes we can keep it as Cu. Cu represents 0.45 here. So this phi represents the speed ratio, that is of 0.45, or we can take it as Cu also. So now with this data we have to find the power which is given by the water to the runner and also the hydraulic efficiency. So these two things we need to find. So let us start finding this. So to find that, we first have to find the velocity of the jet here. So to find that, we have the formula V1 is equal to Cv root under 2gh, where h represents the net head of the turbine. So, but in this problem, the gross head of the turbine is given. So, from this gross head, we need to find the net head. So, to find that, we have the formula net head is equal to gross head minus of friction losses. So, the gross head is of 500 meter, and here it is clearly said that friction loss is about one third times of the gross head. So, one third of gross head is 500. So on subtracting these two values, we will get a value of 333.33 meter, which represents the net head of the turbine. So now this value of h we need to substitute in this formula. So let us substitute it. So the value of Cv is 1 root under 2 into g represents the acceleration due to gravity, which is of 9.81, into h represents the net head, that is 333.33. So let us try to simplify this. So 1 root under 2 into 9.81 into 333.33. So that gives you around 80.869. So we will be getting a value of V1 as 80.869 meter per second. So which is nothing but velocity of jet. Then similarly, let us find the wheel velocity now. To find the wheel velocity, we have the formula phi of root under 2gh, where phi represents the speed ratio, or we can keep it as cu also. So now the speed ratio is given as 0.45 in the question. Let us substitute it into root under 2 into g is again 9.81, and also h represents the same net head, which is of 333.33. Let us try to simplify this. 0.45 into root under, open the bracket, 2 into 9.81 into 333.33. So that gives you around 36.391 meter per second. So this is our wheel velocity. Then comes the inlet angle. So here the angle that is given in the question is the deflection angle, that is of theta degree. Now from this deflection angle we will be finding the inlet angle of vane. To find the inlet angle, we have to subtract 180 degree with the deflection angle. So 180 minus of 165 gives you 15 degree. So this is our inlet angle of vane. Then the fourth step comes. So now in the fourth step, we have to find the work done per second by the runner. To find that, we have the formula work done per second is equal to rho a v1 into v1 minus u into 1 plus cos phi into u, where a represents the area of the jet, v1 represents the velocity of the jet, u represents the velocity of the wheel, and this phi represents the inlet angle. Don't get confused with this inlet angle and the speed ratio. This phi, what we are multiplying with the root under 2gh, is the speed ratio to find the velocity of wheel here. So this phi is the angle that is at the inlet tip, which is of inlet angle. Then that multiplied with the velocity of wheel. So now here the dia of the jet is not given. As the dia of the jet is not given, we can't find the area of the jet here. So for which we can directly take this term, that is the product of area into velocity gives us a discharge. So hence in the next step I am directly replacing this with Q by keeping rho as it is. A into V1 directly gives me the total discharge from the turbine, which is of 2 meter cube per second. So that into, you keep the whole equation as it is. Then let us start substituting the values. So on substituting, here rho represents the density of the water, so which is of 1000 kg per meter cube, which is a standard one, into Q is our total discharge from the turbine, and that is given as 2 meter cube per second. Then into V1, just now we found V1, that is of 80.869, minus of U is 36.391, into 1 plus cos of 15, that is inlet angle is of 15 degree, into again U is 36.391. So let us simplify the whole term. So on simplifying, 1000 into 2 into, open the bracket, 80.869 minus 36.391 into 1 plus cos of 15 into 36.391. So we will be getting 6364090.752. If you do at the single step, at a single shot, you will be getting this value. If you do it separately, you will be getting this value of work done per second. So whatever the value that you get, you just enter it. So that value will be in terms of Newton meter per second, which is nothing but watt. So that gives us the work done per second. But we have to find the power that is required. So for finding the power, so work done per second itself represents the power, because that value we will be getting in terms of watt. If we want to keep it in terms of kilowatt, let us divide the value with 1000. So whatever the value that we got, that value has to be divided with 1000. So on dividing, we will get 6364.09. So here I am getting 6364.007 because I have not kept the whole equation as a single term there. So that value has to be kept in terms of kilowatt. So finally we will be getting power in terms of kilowatt, as we are dividing work done with 1000 here. So now after power we have to find the hydraulic efficiency. So let us find this. So to find the hydraulic efficiency, we have the formula eta h is equal to 2u divided by v1 square into v1 minus u into 1 plus cos phi. So where again u represents the wheel velocity, v1 represents the velocity of jet, and phi represents the inlet angle here. So let us substitute all the values in the next step. On substituting all the values and on simplifying the whole term, let us see what we will get at the end. So 2 into 36.391 into, open the bracket, 80.869 minus 36.391, then into 1 plus cos of 15, then divide the whole term with 80.869 whole square. So we will get 0.973. But as we are finding the efficiency, and efficiency value has to be kept in terms of percentage. For that, whatever the value that we get, that value has to be multiplied with 100. So on multiplying, we will be getting a value of 97.31 as our hydraulic efficiency. So hence the value of eta h is 97.31%. So that completes the type 1 problem.